The autonomous province of Vojvodina, located in the north of Serbia, has always been in the forefront of economic development in both the country and the Southeast European region. With its inherent cultural diversity, reflected in 6 official languages and 23 cohabiting nationalities, as well as a long-lasting tradition in free enterprise, the central research and higher education institution in Vojvodina is the University of Novi Sad, which consists of 14 faculties, 10 centers for interdisciplinary and multidisciplinary studies and research, and a number of scientific, research and development institutes and centers. The Faculty of Technical Sciences is the largest faculty, both within the University of Novi Sad and in the whole of Serbia. It is a vibrant research and educational institution with more than 1,000 employees, over 500 active researchers and teaching staff, and around 12,000 students and 58 spin-off companies. With its long-lasting experience in international cooperation and research projects, FTS has recently been involved in 14 European Framework Programme projects, 7 of which are currently in progress. One of them, the Apostille project, focuses on the development of post-silicon electronics, particularly plastic and nanoelectronics.
This project is entitled Reinforcement of Research Potentials of the Faculty of Technical Sciences in the field of post-silicon electronics and has acronym Apostille. It started with implementation from 1st of July 2010, and the project is financed from the side of European Commission in the framework of FP7 RECPOD projects. This project is intended to reinforce human and infrastructural capacities and to strengthen the research potentials of our team from Faculty of Technical Sciences, University of Novi Sad, Serbia, in the field of nano and plastic electronics. The Apostille project is designed to support capacities and building capabilities for improving the Faculty of Technical Sciences involvement in European research area, especially through the strategic partnership with 6 EU networking partnering institutions: University of Catania and Milan Polytechnic from Italy, Chemnitz University of Technology from Germany, Jožef Stefan Institute from Slovenia, Institute for Sensor and Actuator System and Festo Company from Austria.
Our institute, our faculty is very interested in post-silicon technologies. Since 10 years ago, we started this activity with ST Microelectronics in Catania, and now we had the possibility to interact with prestigious projects like you are cooperating in coordinate like Apostille.
I come from Politecnico di Milano, which is the second largest university in Milan. It has about 40,000 students and it's a technical university, so that's why it's Polytechnic. So they have just technical sciences, so I like Faculty of Technical Sciences here in Novi Sad, but at the university level because they have many departments including architecture and so on. I belong to the Department of Physics and my lab is located in Como, so it's not in Milan, it's in Como. And there we have a laboratory in which we investigate nanostructured materials based on silicon and graphene. I work on graphene, so that's my main field of research. And we actually fabricate nanoelectronic devices made of graphene. I'm involved in this project, Apostille project, as a networking partner, as you said. And my role here is to first establish collaboration with a group here in groups involved in the project, so not only group here in Novi Sad, but also in Slovenia, from Ljubljana. And also we are involved in training of people from Novi Sad. We had recently a visitor, a student, PhD student came to our group. She spent in our group about 2 months and we taught her about nanofabrication of nanoelectronic devices made of graphene. And we are trying to incorporate collaboration here with our main research topics. So since this project is mostly devoted to the printing of different types of material for electronic applications, we are trying to incorporate printing of graphene in this project. We are actually doing this in collaboration with Jožef Stefan Institute in Slovenia and also with a group here. We are using graphene, our main material, which is then printed in Slovenia, and then final devices are made in Como, in our group, in our lab.
I come from Jožef Stefan Institute, which is located in Ljubljana in Slovenia. And Jožef Stefan Institute is a research organization for pure and applied research in the field of natural science. So it's totaling about 800 people. They work in different departments like a department for chemistry, for physics, for environmental science, material science, electronics, and so on. So I come from electronic ceramics department, and our department mainly works in the field of development of new materials and technologies which are applicable in electronics. So these are materials which are used as a bulk material or as layers on the substrate. And we also characterize these materials from the physically, chemically, and also we perform some functional characterization of these materials.
At the time when the initial contacts were established between Professor Stojanović's group and Professor Bauman's group, I was working as a senior scientist with a certain degree of experience in academic and industrial circles in the field we called large area printed electronics, although various terms are used for it nowadays. It's a new area of organic electronics where the basic concept involves using materials based on conjugated polymers with semiconductive characteristics to produce active and passive electronic components, while the technology for applying those materials would be traditional printing technology such as screen or gravure printing. The field gained momentum in the year 2000 when Professor Alan Hager won the Nobel Prize. At that time, I started my studies at the Johann Kepler University in Austria, where I did my doctoral thesis, and afterwards started my own company. The experiences I had in academic and industrial circles were also valuable to Chemnitz University of Technology, so I went there to continue my work. Later, I came into contact with Professor Stojanović, and I joined his group in early 2010, I think, and from then on, we have had an excellent collaboration to our mutual satisfaction. In the meantime, I left Germany and relocated to Switzerland, but I continue to help Professor Stojanović's group and the University of Novi Sad make new contacts.
EPFL je jedan od najpoznatijih svetskih fakulteta u svim oblastima prirodnih nauka I tehnike.
EPFL is one of the most prestigious universities in the world when it comes to natural sciences, technology and engineering. They are among the top 10 universities in the world, which is an excellent ranking. As part of EPFL, the STI School of Engineering is the world's leading school in its field, so it's wonderful to work there as a scientist, and I'm very happy to be there and very glad to be able to connect such an institution with our universities here. The goal is to help further development of science in Serbia and bring in some new experiences. We became a network partner in order to help the project so it can be more successful in the direction of its desired results.
Mi smo postali networking partner iz tih razloga, znači da pomognemo projekat I da to može bolje I kvalitetnije da se razvija u pravcu željenih rezultata.
Apart from European networking partners, the project is supported by regional and national authorities. The Serbian Chamber of Commerce, the Provincial Secretariat for Science and Technological Development, the Regional Agency for Development of Small and Medium-Sized Enterprises, the Office for Local Economic Development, as well as various industrial partners from around the country.
Ja sam došao ovde pre svega da bih se upoznao sa ljudima koji prisustvuju na ovoj konferenciji. Ima jako puno naših ljudi iz inostranstva.
I came here primarily to meet with the people attending this conference. There are so many of our people who live abroad, locals from Novi Sad, as well as a large number of young people. It was very interesting for me to see what sort of problems with science they are facing here and what can be done to help them. The reason I came is that I'm working with the Serbian Ministry of Science regarding the building of a nanocenter in the future. Since my scientific background is connected with this field, I would like to find out what would help people in Novi Sad who are in this line of work, what could be done in the nanocenter to help them in their future research. That's my main goal for coming here.
Šta je moglo da se uradi u tom nanocentru da se njima pomogne u njihovom budućim istraživanjima? To je osnovni razlog mog dolaska ovde.
The project has 4 dissemination partners from Western Balkan countries: St. Cyril and Methodius University from Skopje, University of East Sarajevo, University of Banja Luka, and University of Montenegro. An important contribution to the Apostille project has also been made by our colleagues from the Faculty of Technology in Novi Sad.
Saradnja Fakulteta tehničkih nauka I Tehnološkog fakulteta.
There has been an ongoing collaboration between the Faculty of Technical Sciences and the Faculty of Technology Department of Material Engineering for several years now. In this project, our task was to synthesize ink for printing on plastic substrates with the aim of miniaturizing the already existing components and manufacturing brand new electronic components.
Elektronskih komponenta.
Our first research focus is plastic electronics, which offers the possibility to broaden the horizon of classical electronics due to new properties of devices such as flexibility, lightweight, disposability, low fabrication cost, and a wide range of novel applications. The commonly used synonyms in this area are printed electronics, organic electronics, plastic electronics, or polymer electronics. Plastic electronics differs from the classical one with regard to changed substrates as well as changed materials applied on the substrate. Electronic components and circuits now can be printed on flexible substrates such as foils, papers, textile, etc. Different electronic inks can be used as printing materials.
Printed electronics will never replace classical semiconductor silicon-based electronics due to its lower operating frequency, lower reliability, and larger dimensions of the circuits. However, this new technology has several significant advantages. Firstly, printed circuits are flexible and thin, which offers possibilities for a wider range of brand new applications. The second advantage of printed electronics is very low fabrication cost, which goes down by several orders of magnitude compared to wafer fabrication of classical integrated circuits. Plastic circuits can be printed as newspapers and books, using the roll-to-roll printing process, and considering the low production cost, these throwaway electronics will be completely disposable in the future. Current research and development in the fields of plastic and organic electronics is directed towards manufacturing flexible solar cells, organic light-emitting diodes with more natural-looking colors, and transparent, unbreakable, and flexible touch and TV screens, to name a few.
From a scientific point of view, we are very proud to attend this project. Moreover, we are very interested in the aspect that allow us to cooperate with the young generation in new ideas, in new projects, in new initiatives that should be very suitable to give opportunity to the next generation for making research, to work, to be innovative in a new Europe.
In the past, we were involved in the processing of these classical ceramics. So nowadays, the flexible and low-cost electronics is very popular, and there is increasing interest for these fields. So in order to develop these materials, for example, sensors on textile, or some TVs which could be rollable, so we need to develop new materials, and we need to develop new technologies for this. So therefore we are acting in the field of developing inks for inkjet printing. Inkjet printing is a very promising technology, because we can deposit materials where we want and with a high resolution. However, the inks are not commercially available. So we need to develop these inks from the materials which we produced or which are produced somewhere.
What is directly related to this conference is the so-called organic optoelectronics. It's a very modern approach which shows that not only metal and inorganic semiconductors can conduct electricity and be used to produce components, but also plain plastic. It's a big hit at the moment. Plastic is much easier to process and to make devices from. We can use a simple plotter to place dots on the surface and connect them into an electric circuit. It is something quite modern, and it can make the process cheaper. I've never done any practical work on devices, but I've done work on the fundamental issues regarding this kind of application. I've worked on materials, researched their characteristics, conductivity, optical characteristics, etc. That is the field I worked in for a long time in the United States.
Ono čime se ja bavim i na čemu insistiram, da kažem, je razvoj tehnologija, zato što
What I do and what I insist on is the development of this technology, because the field is very new. There are a lot of problems regarding the very nature of the materials and the technology for applying those materials. What I do is try to solve those problems more efficiently, not by choosing one technology or one kind of material, but rather through the so-called hybrid approach, where you use the best of organic materials, the best of inorganic materials, and the best of steaming and printing technologies. All this is a part of the so-called roll-to-roll production. A comparative advantage of printed electronics is that you can manufacture electronics from ingot to chip in one day, where silicon electronics would take 3 months to do. It looks attractive, but it's not easy, and that's why the success of the technology depends on choosing the right material, substrate and method of application.
Jednostavno, i upravo zato što nije jednostavno, zavise uspeh te tehnologije zavisi od izbora materijala, izbora substrata, izbora načina na koji nanosite te materijale.
Within this project, within Apostille project, we found this collaboration very useful because more people knows more. So, for example, we developed graphene-based ink together with a group from Como, from Italy, and from these inks they develop or they prepare some thin film transistors. On the other hand, also we found very useful collaboration with the University of Novi Sad, where we developed ink. However, we don't have enough knowledge on printing, and therefore we found this knowledge within the consortium. And I think that the breakthrough in the field of this flexible electronic is possible only with a strong collaboration with partners and within such groups like it is now in Novi Sad.
Sama sinteza izgleda veoma jednostavno.
The synthesis process itself looks very simple. We mix together two chemicals. But there are a lot of parameters that influence the definitive characteristics of the ink. For instance, whether the environment is basic or acidic, whether the solution is water-based or alcohol-based, and the amount of pressure used during the synthesis process. All these parameters greatly affect the definitive characteristics and size of the particles, which in turn influence the characteristics of the components being produced. Also, the characteristics of the ink can be varied by adding surface active elements for a more precise control over the viscosity of surface tension.
Radi preciznije kontrole viskoznosti površinskog napona.
I am very interested in printing electronics because it should be open new frontiers in electronics. And I think that should be a very good opportunity to also understand the new phenomena in electronics, to have new products, to have green products in electronics, and the consumable electronics is very timely today, and I think that also that by using new electronics we could improve the quality of lives of people.
Within this project we are trying to envisage a new device for tracing and identification of agricultural products. And to develop this new device we need some new components, and these are being studied and developed in collaboration with the Faculty of Technical Science in Novi Sad. This obviously require new studies, new technologies that have been acquired within this project. We are trying to understand, to develop new techniques and then to realize these new components. So conjugating these two things, the idea is to come up with a cryptographic system in which you can hidden the information so that only the owner of the product knows exactly this code, and this can be used for safe reason and to guarantee a given product, for instance an agricultural product.
The first challenge is actually to make a working transistor out of graphene, whether it's printed or made in another way. Because graphene is a very nice material because electrons and holes in it flow very easily. We say it has a much higher mobility than silicon. It's about 60 times more. But the problem is that it doesn't have a band gap, so making a real transistor out of graphene is not so trivial task. And the main challenge that we face now with using graphene in printing is to make a stable and printable inks, because graphene is not so simple to handle when it comes to the liquids, to the dispersions, because it's highly hydrophobic material. And this is the first challenge that must be solved. And secondly, the other problem is that once when it's made, we have to make really high performance transistors if you want to compete with silicon technology, and that's not really easy. Because even if we would be able to reach performances of silicon transistors, which dominate market now, this wouldn't be enough, because to change technology from silicon to something else, you really need to be an order of magnitude better, and currently with graphene that's not possible. Graphene is currently better in terms of speed. We can make very fast transistors, but that's more or less it.
Our colleagues from Serbia will be coming to our institute to complete a part of their doctorate there. They will be returning to their base university to earn their doctorate degrees here. We have to be careful not to cause the so-called brain drain, young people leaving entirely. We should keep them in Serbia while providing them with outside experiences and education, so they will have the possibility to receive education, gain experience, and bring it back here. My colleagues and I are working on developing new sensors with conductors printed on a flexible surface, and we are trying to use the flexibility of the surface to make new structures and geometric shapes, which will then be used to produce simple but very sensitive sensors. We hope to develop capacitive sensors for detecting chemical substances, for instance pollution, etc., or inductive sensors which can be used in valves and similar devices. On the screen we can see an inductive position sensor with two printed conductors whose couple changes depending on the angle, and this program enables us to calculate with great precision the self-inductance and the mutual inductance of the conductors.
Kako samoinduktivnosti provodnika, tako i njihova međuinduktivnost.
Our second research focus is nanoelectronics. Nanoelectronics refers to the use of nanotechnology in electronic components. Nanoelectronic structures have dimensions below 100 nanometers, and they work with ultra-low current and low voltage, and they are specific due to their operation at near theoretical limits: fundamental, technological, architectural, and algorithmic. Developments in nanoelectronic devices are also driven by the ability to produce finer and better nanostructured materials and to perform their successful characterization.
Nanotehnologija je specifična zbog veličine na koje se fenomeni odvijaju.
Nanotechnology is quite particular due to the scale on which the phenomena are taking place, as opposed to microelectronics, where most elements are at the micrometer level, that is, 1/1000th of a millimeter. Nanotechnology takes place at the nanometer level, that is 1/1000th of a millimeter. A completely different set of rules are at work on such a scale. It's a few 100,000 atoms, not even a whole particle, and different laws apply. This enables improvement of the existing characteristics of microelectronics and also the discovery of brand new characteristics of materials. The biggest problem is the size of the scale. It's 1/1000th of a millimeter, and calculating or determining anything with any precision at such a small scale is very difficult. And that's the biggest problem, how to determine something precise, reliable and reproducible on such a small scale.
Tu su u stvari najveći problemi, kako odrediti nešto tačno, pouzdano i reproduktabilno na tako malom nivou.
Ja radim u oblasti nanotehnologije, a tačnije oblast rada...
I work in the field of nanotechnology in the area dealing with the development of new materials, namely nanocomposites, which can be used in the fields of electronics, microengineering, bioengineering and biomedical application.
Elektronike ili bioinženjeringa, biomedicinskih aplikacija.
Our research potentials have been additionally reinforced through recruitment of free incoming experienced researchers and through purchased and installed new research equipment in the field of nano and post-silicon electronics, inkjet materials deposition printer for fabrication of components, nano indenter for characterization, and high-performance computer cluster for modeling and simulation.
Here we have the Dematic's inkjet printer used for applying flexible electronic circuits. The surfaces in this case can include various materials, which are usually flexible and up to 5 centimeters thick. The printing resolution is 1x1 micrometer, while functional materials are solutions based on nanoparticles, conductors, dielectrics, isolators, and semiconductors. The printer can produce active and passive semiconductive components, including inductors, condensators, and resistors, as well as antennas and resonators. New technologies are also introducing the use of photovoltaic devices, which represent a combination of dielectric, conductive, and various active materials, which are specifically designed for their intended purpose.
Sve izgleda jednostavno, sve izgleda atraktivno, a u stvari nije.
It all looks simple and attractive, but it isn't. There are so many parameters that can influence the success in terms of the materials, market, and technology, But when you mix it all into a breakthrough product, then you're on the right track. The technology started developing in the United States, continued in Europe, and it comes from the East. Killer application display. It's not the future anymore. This is a 2-year-old product. We thought that new technology would create a new product and a new product would create a new market. That didn't happen, so we are trying to revise the dogma that new technology does not automatically create a new product and a new market, but that we should introduce the new technology to the existing market. The rules have changed, and that will delay the solution, but we will definitely not give up. We shouldn't give up. That's why we need new forces, especially people who have experience in classical electronics. Because with the knowledge of what silicon electronics offer and what printed electronics offer, when you combine these two things, you don't need a new market. You need a new approach to deal with the problems that are already there.
Kad se te dve stvari spoje, onda ne morate da imate novo tržište, trebate da imate novi pristup rešenju problema koje su već tu.